Hi, and welcome back to another Level 3 differentiation video. In this video, we're going to focus on an idea and theme called related rates of change. We know differentiation is the process of taking a function, an algebraic rule, and turning it into a grading function. And we need to be familiar with all the types of notation. These are called rates of change, is the official terminology for a gradient. In many situations, as one variable changes in relation to another, a related variable also often changes too. For example, if we can imagine a circle that's increasing in size, we know that the radius of the circle is increasing, say for example at a rate of 3 centimeters per second. We also know that the area is also increasing at a certain rate too. So the area is that related variable that is related to the radius changing per second. Right, we're going to use a technique called the chain rule, and we're going to use this to determine derivatives that involve now three variables. And here is the chain rule. dy dx, which is our standard gradient, is equal to dy dt, which is the change in y with respect to time, times dt dx, which is the change in x with respect to time that's been flipped upside down. And as you can see quickly that the dt's kind of cancel out, leaving us with just dy dx. Oh, this is called the related rate of change. And we'll show you how this works with an example. Right, so here's the example. The radius of a sphere is increasing in size with a given rate of 3 millimeters per second. What is the rate of change of the volume when the radius is 16 millimeters? So the radius of the sphere is increasing in size with a given rate of 3 millimeters per second. Well, we could write this as change in radius over change in time, or change in radius with respect to time, is 3 millimeters per second. Millimeters per second are the units. Right, we're asked to find what is the rate of change of the volume. Now, quite often when they ask for rate of change without any other information, we're talking about rate of change with respect to time. So time is quite often that third variable. So we need to find the rate of change of volume with respect to time. Right, well that's going to be equal to something times dr dt. Well, the something is going to be dv dr. And if you can ever think about it, the dr's are going to cancel out, leaving us with dv over dt, which is what we need, the change in volume over the change in time. That is the rate of change of volume. Okay, so since we already have dr over dt, which is already worked out above, what we've got to work out is dv dr. So to do that, let's start off with the volume of a sphere. The volume of a sphere formula is 4/3 times pi times radius cubed. So let's work out dv dr, which is the change in volume with respect to the radius. So here's what we do. We bring the 3 out the front, times it by the 4/3, and times by pi, and then we take the r cubed and subtract 1 off the power, which simplifies down to 4 pi r squared. Right, so we're now ready to work out dv dt. dv dt is equal to dv dr, which we just worked out as 4 pi r squared, times by dr dt, which we knew earlier, that was given in the story, which is 3, which simplifies to 12 times pi times r squared. So this is the change in volume with respect to the time. Now, the question said, what is the rate of change of the volume when the radius is 16? So we need to grab 16 and substitute that into our dv dt. And we get a dv dt value of 9,650.97 millimeters cubed per second. Don't get too caught up in the units. Not vital that you understand units really. Great, thanks for watching.